Hello everyone and welcome to this new video where we are going to present a quite fascinating paper from Paul Dirac from 1929, where he actually discusses some aspects of what we call today the Dirac sea, and some other aspects that I think are often ignored or not necessarily talked about when people talk about Dirac's work on the electron and the positrons and so on. So let's have a quick glance through, shall we? So the title of the paper is A Theory of Electrons and Protons. So again, it was submitted by Paul Dirac, and then it was published in 1929. So in the first part of the paper, which is on the nature of the negative energy difficulty, essentially Dirac tries to, put forward his equation. This W here corresponds to a sort of kinetic energy operator. And then the other parts like rho 3, rho 1, etc., are kind of matrices that Dirac has introduced in his particular equation. And the equation is already complicated looking because Dirac directly considers an electron in an electromagnetic field. And so here we've got A naught, which corresponds to the scalar potential, and the vector potential here, A. Sigma has a famous kind of Pauli matrices, and basically that's it. So what actually Dirac notices is the following. So he notices that by reversal of the sign of the potential A and either the radial wave, we can have basically a negative energy E. That's kind of the idea. So if we play around with the signs in the equation should somehow be unchanged, but then we would change the sign of the energy. And then he actually here, this could be something that would be found classically as well for relativistic Hamiltonian theory, and that's how that's what the Hamiltonian theory would give you essentially in relativity. And what he notices is that in the term on the left, essentially you've got an ambiguity with regards to the sign of W. So this equation is going to be satisfied regardless of whether W is kind of positive or negative. And so this kind of gives some amount of freedom for this, which is problematic. Now, one of the things that he mentions is that basically there are two possibilities. W plus E A naught has to be larger than or equal to mc squared, or W plus E A naught has to be less than or equal to minus mc squared. Now, the point is that he does mention rightly that most of the time when we find situations like this, we just get rid of the negative part and we claim that it doesn't make any sense. But here he says, well, we can't do that because my theory, and in fact the quantum theory, when we play a bit with it, we are going to see that in an electromagnetic field, we can actually have states that oscillate kind of back and forth, these positive and negative energy states. So we can't claim that in negative energy states are somehow never accessed. They are accessed at least as part of the as far as the quantum theory is concerned, and therefore he reaches a conclusion a bit lower, that we can't ignore these negative energies. And then he says that if we try to actually see how these negative energy states actually behave, well, in most circumstances, they actually see that the trajectory is a possible trajectory for an ordinary electron with positive energy moving in the electromagnetic field with reversed sign, or for an electron of charge plus E, and positive energy. So essentially, they say that these negative energy states appear to correspond to essentially positive energy electron states where the charge would be simply reversed. And so thus an electron with negative energy moves in an external field as though it carries a positive charge. So that's kind of the idea. What is fascinating, and that, to be honest, I didn't know before reading this article, is that actually people thought at the time that there was a connection, therefore, between negative energy electron states and the proton, so which was at the time then the nucleus of the hydrogen atom. And so, in the rest of the article, which then I kind of leave to you, there is a whole range of discussions about how these negative energy states could explain actually the proton. And then there are various challenges that Dirac mentions about the fact that how do we explain the asymmetry in the masses, for example, between electrons and protons and so on. And in fact, it does put forward some ideas about how we could justify these asymmetries, etc. Now, famously in this paper, he also talks about the Dirac C idea, whereby by using the Pauli exclusion principle, we can imagine a sort of sea of electrons, all of negative energies, and then a vacancy in that particular sea of electron ends up being basically acting as a positive charge of positive energy, kind of moving in in the way an electron would do. But here again, not necessarily in the way an electron would do, because there is a possibility in this paper that this could model also a proton. So basically, I think I'm not necessarily going to go way further. I'm about kind of halfway through, and it proposes kind of a solution with this Dirac C idea, and basically this idea of holes in the Dirac C. Okay. So again, personally, so some people would say, in usually in basic introductions to quantum field theory and relativistic quantum mechanics, people would say kind of the Dirac C is a fairly kind of obsolete idea now. It has been superseded. Maybe it has, but I do find it incredibly insightful nonetheless. And I think this paper is very interesting to read for that reason as well. We can see that they try to foresee the potential difficulties with these ideas and so on. So if you're interested, I'm going to put obviously a link to this article in the description of the video. And if you've got any questions or comments, please let me know in the comment section. Otherwise, see you in the next video.